Hey, hi guys. Sorry, I kept it on live without talking. So today we'll just quickly complete the logistic regression discussion that we started yesterday. Um, what I did actually, I'm there from 7, but last few minutes I've been spending on understanding. So when we were actually discussing between friends on the AML topic and discussion and stuff, he raised a point saying, see, so I told him that usually my approach to understanding AI/ML and stuff is to get into the detail, so that once you know the underlying detail, your capability to apply it is good. Your capability to understand not only what it is, but you can also understand why it is in place and why people have thought through in that direction. Um, Opens up a newer perspective of how you can apply, or maybe you could also think how you can optimize it basing on the um, requirements that are there. So that's always my thinking. This is the discussion we had, and then he's like, he told me, see, forget about something complex like generative AI and some blah blah blah. Let's talk about logistic regression. Even for logistic regression, we don't exactly know how those equations are derived and stuff. So that was the comment. I was like, um, so I should understand it now. And yesterday when we were talking, actually, I said like, this is how the logistic regressions loss function is going to be. I'm like given the formula. I want to get into the details, saying, and I also said linear regression is logistic regression is both related, where linear regression is part of the logistic regressions. Um, Sigmoid functions equation and stuff. This is what we were talking, right? So I just thought, let me look at the detail, but it's not that much. But we'll go through whatever material that I've covered and stuff, so that you guys are also on the same page with your understanding. So this is going to be today. It's going to be very quick. I need to wrap it up quickly. We didn't write anything on logistic regression, which is very nice. So coming to logistic regression, I said it is a classification algorithm, but it says regression. So what does regression mean? We have already discussed regression means continuous values, right? So when we say continuous values and we want classification is more like classification. So we apply classes like class 0, class 1, class 2, class 3 kind of stuff. So where for example, if you have two classes, class 0, class 1, class 0 can be apples and class 1s can be oranges, or class 0 can be um, class 0 can be disease, class 1 can be no disease. So as simple as that. So it could be anything as classification, right? But as I told you, every see, machine learning, I think the way we started off as recognizing the patterns of in the data, and then and putting that pattern into a certain equation, and that equation in turn taking feeding in unknown values, and that unknown values predicting certain values, the unknown values being fed into an equation, and that predicting what could be the possible outcome of that unknown values that are coming in, right? So that, and for that, it's this is all covered in linear regression, right? Now coming to logistic regression, the output is expected to be binary, 0, 1. What we know is linear regression, right? And linear regression values will be, so usual linear regression is an equation And so if you either take a straight line or you use a curve or whatever you do on the input x values, we always we don't know what could be the possible input x values, correct? So we know certain values. Basing on that, maybe the graph is like this. But if we say that we don't know what are the possible x values, the possibility is x can be or x or either x or y, both of them can be ranging from anything. It depends, like features, it depends on the feature, right? The feature, if the feature says number of wheels, it could have a range. So you can't have obviously you can't have negative number of wheels. You can have positive wheels, but you can't have 100 wheels to vehicle. Doesn't make sense. Or even bigger numbers like 1,000 wheels per vehicle is not possible. So technically it has a range. It will have some range, which again is not defined, saying what is should be the range kind of stuff. But there is logically there is a range. But whereas y, we don't know what y value can be, right? Y value can, as I said yesterday, it could be bank number, it could be size of a substance or something like that in nanometers. So the number could be bigger, right? So number could be, do we know what is the upper limit or limit or range of the numbers? We don't know. So considering that fact, the regression values usually are not bounded or are within a range in general sense. It differs by use case by use case. But the expectation of an algorithm when we build it, we think saying it should accommodate no range restriction. So when I say no range, it's simple. It is like on the real number, it is on left and right side, right? The leftmost is minus infinity and rightmost is infinity, correct? So the linear regression's outputs are targeted to predict minus infinity to infinity. Where we fit in depends on where we would be, depends on the equation that we're picking, and it also depends on uh, it also depends on inputs that we're providing to it. Based on inputs and the equation, it will vary. Now coming to logistic regression, so linear regression, y predicted will be, or not will be, could be between minus infinity to plus infinity. There's nothing called plus infinity, but infinity, but to distinguish minus infinity to plus infinity. Whereas when you come to a classification problem, what we are expecting is logistic regression and let's say binary classification. Then we say it is from 0 to 1. Matter of fact, it is more 0 or 1, but because we are going with the probability, we are not just saying 0 or 1, we predict the probability, and the probabilities are between 0 to 1, where we could take a call saying 0 to 0.50, 0.5 to 1 is 1. So what we want to use in our logistic regression is underlying is linear regression, but what we want is logistic regression is 0 to 1. So either we need to map minus infinity to 0 comma 1, or 0 comma 1 should be extended to become minus infinity so that the equation can fit in, right? So what that's the approach that people had. So to scale logistic, to scale 0 to 1, and let's say we go this way, 0 to 1, if you want to take it to minus infinity to infinity, there are certain functions that are could be applied on probability 0 comma 0 to 1 range numbers, and extend them to minus infinity to infinity. One such function that people use is odds ratio. Odds ratio is nothing but um, probability usually gives you what is the probability of positive outcome of it, and if the positive outcome is divided by the negative outcome of the same value, then that is called the odds ratio. Okay, so that means how much positive can we predict, how much positive probability is there relative to the negative probability. For example, if you have 10 apples and 10 oranges, something else, and we don't include the other classification, we're looking at classification from one perspective, right? So it's like, okay, forget about oranges. We have apples and then we call it apple, or we call not an apple, right? So out of 10 apples, if we say 6 apples, we have probability saying these are apples. For the other 4 apples, either apples, it says these are not apples. So the positive outcome is 6, and the negative outcome is 10 minus 6, right? So it is 6 by 4, correct? So it will be 3 by 2, it's 1.5. So if the apples predicted are 0, and 0 by 1 minus 0, it is 0. If the apples predicted are 10, then it is 0, sorry, 10 by 10 minus 10, infinity. So the value range of this odds ratio is positive comes by 1 minus or total outcomes minus positive outcomes, right? If it is assuming, if you put it in probability numbers kind of stuff, it will be like P of E by 1 minus P of E, right? And this will range from, and assuming this is P of E, and this odds ratio will range from 0 to infinity. When we say 0 to infinity, but where we want to reach is minus infinity, infinity. So one value, one function which will actually scale a given numbers to from minus infinity to infinity on given these kind of numbers, right? 0 to infinity or whatever, is to go with logarithm. Okay, we'll discuss more on it. Logarithm of these numbers 0 to infinity will be minus infinity to infinity. That means log of P of E by 1 minus P of E. This is ranging from minus infinity to infinity. How? If you look at logarithms, log of so to start off, log 0 is not possible, because, okay, let's talk of logarithms, right? To understand logarithms better, logarithms is nothing but, if you want to show a given number as a multiples of another number, so that means 100 can be looked at as multiples of two tens, that is 10 into 10, right? So that means log 100 with base 10 is equal to 2, right? Okay, so similarly log let's say log a base b is x, or let's say is I. That means b power I is equal to a. So that means if you know a number and you want to represent, if you know a number like a, and if you want to represent that number, if you want to find out, um, given that number, what multiple of another number gives you that number. Like example, I said 100 to the base power. Now 100 is multiple. 100 is what power multiple? What how much multiple of 10 is 100 is 2. How much multiple of 10 is 1000? 3, right? So like how many multiples of 10 can be used? Similarly, how much multiple of 10 is 0.1? Right, 0.1 we can write as 10 power minus 1. That means 10th power, what we give the value, that is actually is nothing but, so to derive 0.1, how much power of 10 should be used? Then we say log 0.1 base 10 means it's minus 1, because 10 power minus 1 is 0.1. So if log 0.1 base 10 is equal to something, means 10 power this value will give you this value. Okay, not sure how you guys can look at it, but that's logarithms. Okay, simple logarithm is simply showing that given a number, um, and given a number, and if that number needs to be represented in multiples of another number, like let's say um, I think I mean this is all I'm giving you more, but nothing wrong to learn. So it's good to learn, because we feel they are complex, but they are actually simple. Just that instead of explaining all this for this long, people use a simple term logarithm, but we should understand why the way and where to use it, right? So um, I have uh, I have like 100 chocolates, and I decided to give um, or I have 100 chairs. Okay, I think this is also complicated, but okay, let me give it a try. I have 100 chairs. Okay, I want to see um, what is the best possible way that I can, or I want to see how many um, how no. Oh, this is interesting, man. We're trying to say where will somebody try to use logarithms, right? What is the practical use of logarithms? I thought you will say arrange the um, by 10 is okay. That makes sense. At 10, but when will you get 10 by 10 by 10? Okay, let's ask ChatGPT once. It's a good question to ask, actually. Oh shit, I'm not sharing my screen. This is funny. I've been writing without sharing my screen. Okay. Where do we use in real world? Provide an example. Okay, you guys can't see. I'll just move this. We use algorithms in real world. Provide an example. Algorithms are used in various real world applications, finance and economicals. And are commonly used in finance and economics to calculate compound interest. Time it takes for the investment to double. Um, how is that? For example, if you want need to get 100, yeah, makes sense. So, for example, if you want to get 100 percentage and you get interest at 6%, how many multiples of 6% um, would become 100? Like, what power of 6 will become 100, right? Uh, Makes sense. Does it really make sense? No, doesn't make sense because x is there and to 6% is there, then it is into 6. It's not into 6 into 6. 100 rupees is there, you get 6%. Interest is not 6%, 6% is 0.6. Yeah, makes sense. That's it. Yeah, so 100 into 0.06, 6% means 100 into 0.06. That's your interest. Or you can say 1.06 into 1.06. And again, next year, you multiply it 1.06. So you take 1.06 as base and 1.06 power. That's what it is written here, right? 1 plus r power t. So 1.06 into power watt will give you 100, will give you like how much in how much time it'll get double. Yeah, makes sense. There we can use it. Acoustics and audio engineering algorithms are used to measure sound intensity and express it in decibels. So I think for representation purpose makes sense because he says the values are um, like earthquake. It's there below it. Person approximately 31.6 times more. So somebody says 6.5. So that means it's log. I mean, the numbers are pretty big, and instead of giving the big numbers, to put them down to a smaller number, they'll and for people's understanding or communication between different parties, they might use a base of maybe something, right, and then communicate. So yeah, that's also makes sense. Like something like 100,000 or something like that, and then we say it's base 100 if you say, or base 10 if you say. Also, it will say 5. Actual number is 100,000, but you don't want, for calculation purpose and stuff, you don't want to use 100,000. Then it will become then you can use it as then you can actually store it as 5. But actually what 5 means is actually a logarithm of base 10 applied on that particular number gives you 5, and the actual value is 10 power 5. Makes sense, makes sense. Similarly, in chemistry, to see how much moles are there and something like that. Like anyways, it's all boiled down to numbers, right? And has hydrogen ion concentration of 10 power minus 3 moles per liter. Oh, okay, that's what pH means. But instead of telling us number like 10 power minus 3 or 0.0001, they call it 3. But actually what it means is 10 power minus 3. It's actually used for communication or data representation instead of showing a very big number, a very small number kind of stuff. Here we will put it into a common number, but underlying, to get the original number, again we need to go back saying, okay, this number is logarithm of the real value with certain base. If we know the base, then if we take the base and apply this number as the power to it, we'll get the original value. Makes sense. Okay. So to some extent, okay, real world application we need to see when and where we will do it. But going back, that's with the logarithms. I think we are deviated far away. Generative AI and supposed to be LLMs and stuff, and then we came to machine learning AI. We came to machine learning to linear regression to logistic regression to log functions, and now we are talking about what is logarithms and stuff. I understand, but let's say today is a deviation, and then we want to learn more. Our curiosity is kicking in, and we want to learn more of it. So this is what is the story of logarithms. So what happens is this is logarithms, right? So now going back on how logarithms is minus infinity infinity. So log of you take anything for the log of x with some base b to be 1, the x needs to be 0, correct? Because no, sorry, x is equal to 0 is not possible. That's what I'm trying to say. If a log of x is equal to 1 is if the base is b, then b power 1 is x is equal to b. So okay, how does when does the log value become 0? Not possible. Okay, when does it become 1? Log value of something becoming 1 when the x equal to base, right? um when is it equal to 0? Not possible, because b to the power anything can't make it 0. Okay, so that's not possible. um when does it become infinity? when when x is infinity. I think we should take this down. um minus 10, let's say minus 1, when x is equal to 1 by b. Minus infinity. B power minus infinity. That's nothing but 1 by b power infinity. When equal to 1 by b power infinity. Correct? X is infinity. Not is equal to, yeah. That means b power infinity. That is x is infinity. So logarithm becomes 1 when no, not x is equal to b. uh, when no logarithm of e is possible, it's not possible, this is wrong. X is equal to 1. At 0 it becomes 1, at 1 it becomes b, and at minus 1 it becomes 1 by b, and as the negative numbers increase it will go to minus infinity, but it doesn't go to 0. 0 is not possible. So from 0 to 1 is where it goes to negative numbers, it goes down graph, and 1 to above it keeps going to infinity. This is the understanding. Let's look at the blog which is explaining this. Actually, I should have started there because it would be much more clear. So does it say the graph? Does it say? Okay, fine. So this one. Okay, this is clear, right? That's not okay. That's okay. The blog and stuff we can put it on. So this is clear. So it is logarithm is ranging from minus infinity to infinity. Okay, that is clear. So logistic regression gives you the expectation is to get certain probability, and that probability uh, which is range of 0 to 1, but the linear regression is minus infinity to infinity. So in order to map these two, what we need to do, we should apply certain function on either sides. Any side is okay. It says to say that both of them are matching. So you predict, so your values of linear regression are minus infinity infinity. Now what happens if you want to map a certain value in, so you apply a linear regression, you get certain value. Now basing on that value, how do you say whether this particular probability of that particular x features x1 x2 x3 is what in the classification? So that is what we need to arrive at, right? Simple. So how we can set it is this minus infinity comma infinity that is there, that we should map it to 0 comma 1. How do we map it? This is how we can map it, right? So now this function, that is log of p of e by 1 minus p of e is infinite minus infinity. Now we can equate this with yp. Yp is nothing but actually w1 x1 plus w2 x2 so on, right? So wi okay, wi into xi plus assume some constants. So uh, now let's just call it z. Okay, but this is good. But what we want to arrive at, what we want to predict, this is good, but what we want to predict is not z, right? As if in linear regression, in logistic regression we want p of e, right? So how do you get it? We can derive it using that equation, right? So here we are using log base power e, let's say. Then as per what I explained here, right, log a to the base b is equal to I, then b power I is equal to a. Similarly, log some value to the base power e is equal to this y z. Then what happens? Not capital Z, just make it small z. Then what happens? let's take that equation, the above equation, and then say P of E by 1 minus P of E is equal to, the base is E power Z. So it's E power Z, correct? Correct. And so, I mean, solving this, not a complex thing. So, um, 1 minus P of E, I mean, I'm just trying to make it simple by, I'm doing reverse of both sides. So this is 1 by E power Z, correct? Now that is now that is 1 by P of E minus 1, right? So here I'm dividing 1 by P of E minus P of E by P of E. P of E by P of E is 1, right? Okay, let's make it that way. What is the big deal? By P of E. Okay, I'm distributing here, equal to 1 by E power Z. So what happens now? This is minus 1. So this goes here, it will become plus 1. So 1 by P of E is equal to 1 by E power C plus plus 1. So this is nothing but E power minus Z plus 1, correct? So P of E is equal to 1 by 1 plus E power minus C, which is nothing but our sigmoid function. So what we want to predict in logistic regression is P of E. How do you get it? We calculate for given features x, x1, x3, we calculate Z, that is nothing but yp, y predicted, and that we map it, put it in an equation, which will actually kind of map minus infinity to infinity range values to the required 0, 1 values that we need. And basing on varying the minus infinity values for a given point, we vary the corresponding 0 to 1 points value. Means it could be 2200 or something like that in the linear regressions YP product. YP and 2200 will be mapped down to the corresponding probability using this sigmoid function kind of stuff. So, and then what we do, we and for given x features, let's say the value is 2200, and we'll keep the 2200, yp is 2200, and we keep this 2200 here, like 1 by 1 plus e power minus 2200. It will give certain value, and if the certain value is not matching with the actual probability, right? So that means the values are the value is expected to be closer to 1, let's say, but the value is closer to 0. Then we change the weights in a way that the 2200 either should reduce or increase, and we tune, we again do the loss function. We can look at the gradient descent and stuff, and adjust it, come up with new W values and stuff, um, and then we can fine tune it. But the um, but what happens is you are changing 20 to 100, but actual value that needs to be stored is the expected value is 1, and you let's say you're 0.3. Then your um, so loss for logistic regression goes like this. So expected value is 1 and output is so p, then loss is 1 minus p. And similarly, if expected value is 0 and output is p, then loss is p or minus p. So basing on the input value, the output or the loss is determined. If the expected is 1, this is the loss. If the expected is 0, this is the loss, kind of stuff. So again, these values are represented by probabilities. That means these values will be 1 minus, so like p output itself is within scale of 0 comma 1, correct? And this will become same. This will also become 0 comma 1. And this will become minus 1 comma 0. So the value scale is pretty small. So even here, what we do is uh, instead of multiplying with 0.2, 0.3 kind of stuff. Anyways, to put this loss function into um, one single equation instead of having two different equations, in order to put it into one single equation, what we can do is, let's say the output expected is, let's say we call it as PA, okay, P actual, and this is PP, P predicted. So then we can actually say PA into 1 minus P plus this is 1 minus PA, because it's 0 to become 1, we should say 1 minus PA, and then it's minus PA. So this is the last function. But what happens, the 1 minus P and 1 minus, okay, let's say if it is predicted, are the loss functions, and excuse me, if they are the variables, right? PP is the one where we have W coming in 1 plus E minus Z, and Z in turn has WX and all that stuff, right? So those are the variables. And if those variables are in that range of 0. The overall your loss function will become um, pretty minimal, right? So in order to again um, in order to bring in a proper higher value or something like that here, what we could do is like you remember in cost function we did squares, right? Similarly here what we do is we apply logarithm again in order to make the derivations and math easier, especially because the p value is 1 by 1 minus c e power minus z, um, and to handle that, the applying a logarithm will be a much easier way for calculation purpose. That's all. Let's ask ChatGPT also once. Why do they use logarithm in logistic loss function? Numerical stability penalization misclassification, maximum likelihood estimation MLE, like mean square error, it says maximum likelihood estimation. um, okay, the logistic regression model is often trained using maximum likelihood estimation MLE, where the goal is to maximize the likelihood of observing the actual binary outcomes given the predicted probabilities. By taking the negative logarithms of the likelihood function, we obtain the log loss function, which we aim to minimize during the training. Which says its definition of logistic regression is what he's trying to give here, but more on, I think second point is so logarithms help improve numerical stability, especially when dealing with probabilities that are close to 0 or 1. Taking the logarithms of probability ensures that the loss is well behaved and does not explode to infinity as the predicted probabilities approach the extremes of 0 or 1. Okay, penalizing misclassification. The logarithm function is concave, meaning it penalizes large errors more than small errors. This property is desirable in loss function because it assigns higher penalties to large deviations between predicted probabilities and actual outcomes, leading to more robust model training. Okay, so this would be the final loss function. Again, why we do the um, average and stuff, you guys already know it, so there's nothing new to learn there. But all the remaining is gone. Is equal to 1 by n sum of pa is nothing but yi, but yi into ryi log pi plus 1 minus yi into log of 1 minus pi. This is what happens with the chat gpt. You say that you're wrong, it immediately says yes, I'm wrong, and it gives you an answer. But at times what happens is its answer is the same. Okay, so it cross validates, and but if it is correct, what happens is it's actually same thing. It's like maybe it doesn't want to hurt your ego or something like that. Interesting, right? Yeah. Okay, that's it with the log loss for this thing. Okay, let's quickly look at okay, how are weights calculated in um, coefficients or parameters are calculated. Mhm. So it's the same thing, I think. That's the last function. How it is, we need to derive the gradient. This is okay. So we derive the loss basing on the variable. So wj is equal to wj minus derivation of loss with wj. And what does he give? Derivation of loss of the j will become, so yi into 1 minus yi into xij minus 1 minus y into yi xij. That means that's the derivation of this particular loss function with respect to wj, it seems. Okay, sounds good. I think we could. We've covered logistic regression, so I think you can understand. So again, same story as gradient descent. So we pick up random values of the one which is represented as beta here, and then we calculate the loss function for the given x1 x2 using this particular beta one, and then we see what is the loss, and then we calculate the new beta by doing the descent, and the by keeping in calculating these values, um, and arrive at new beta, and then we repeat that step. So the learning rate again helps in the steps that in which the particular w's will be changed, and then finally we'll come to an optimal w where the loss function is minimal. That's all. Same logic as same gradient descent algorithm that we have applied in linear regression, same will be applied here. Only difference is the differentiation are the cost function, and loss function that we use in linear regression is different to gradient descent, so to linear logistic regression. So the derivative of it will be different in linear regression and logistic regression. That's it, guys. So that's it for today. We'll continue tomorrow. We'll start off tomorrow with a plan on what do you wanna cover, and what are we going to do stop this. It's already 7 days, and then we've reached from introduction to AI to intro to machine learning, linear regression, and logistic regression. But I think we are getting to enough detail to understand it well. So even though it is going slow, I think we are in the right track. I'll try to accelerate it's because, especially because for me it's more a revision, which I've already studied these concepts. But the bad part I see is because even though I studied this to this detail previously, for some reason, I mean, as per my logic, I say if you understand the fundamentals of it, you should remember it pretty long period. But at the same time, we should also have application of that particular thing. Otherwise, if for linear regression we might have used few times, but logistic regression not many times, right? We use other algorithms for it. Once you don't use it, the the small details in that particular algorithm is tough to remember. But I hope now, basing on the journey or walkthrough that we did now, I think I believe I'm gonna remember this for longer time. Okay, let's see. Okay, thanks, guys.